All right, here we go. It is a holiday in the US, so doing things at a slightly different time from a slightly different place, but in general, excited to get started or continue with simulating a quantum computer, and in particular, building up to the quantum Fourier transform, and then eventually Shor's algorithm for factoring numbers efficiently on a quantum computer. And so last time fought through some API changes that we needed in order to support quantum gates that didn't operate on adjacent qubits in a circuit. So previously we had an API that was basically tell me what the gate is. The gate knows how many qubits it takes, and just tell me where it starts, like what the first qubit it applies to is. And then if it's a 3-qubit gate, and you say it starts at 1, then 1, 2, and 3 are the gates it's going to apply to. And when looking at the quantum Fourier transform, it became clear that we were going to need a generalization of that. So we updated our API, we updated the function, and we ran into a particular bug, which I didn't have time to resolve yesterday before finishing, which is fine. I actually like to have a bug to solve right at the beginning of a coding session because it gets me right back into it. I find it a lot harder to like start the next step of a project when I'm like faced with having a big design challenge or something. It's like I would rather just do something that's like pretty much tactical problem solving, and use that in order to kind of get back into it. Hey Cumatiziert. I feel like I'm not parsing your name right. How's it going? We are not sure if you were here from the beginning, but we are simulating a quantum computer, and we're going to start with debugging an issue that we had last time when we updated our the ability to add gates to quantum circuits. We now give it not only the gate but all of the input qubits that it applies to. We wrote out this function, and when we run our tests, we run into some issues. So let's check that out. So basically, we want this 2-qubit circuit here to operate correctly, and it is very much not doing that. So basically, the way that this simulated quantum computer API works is we say, look, I want a quantum circuit, which is going to contain a bunch of gates. I want it to take 2 qubits or a 2-qubit register as an input. So this is going to be analogous to, in a regular computer, some logic gates that operate on, either 0, 0, 1, 0, 0, 1, or 1, 1. A quantum circuit can operate on superpositions of those, but those still form the basis for the inputs. And then we add a gate to it. So in this case, we add a single C0 gate to it, which is a controlled NOT gate. So it uses the first bit to control whether to NOT the second bit. So for instance, 0, 0 should get mapped back to 0, 0 because the first bit was 0, so it doesn't NOT the second gate, so it keeps it, or the second qubit, so it keeps it 0. So 0, 0 goes to 0, 0, 0, 1 goes to 0, 1 for the same reason. But then 1, 0, and 1, 1, we are saying we want to NOT the second gate. And so 1, 0 goes to 1, 1, and 1, 1 goes to 1, 0. And so that part of the test is still working, but then I do a slightly more complicated 2-qubit circuit where I start with a C0 gate, and then I use these Hadamard gates, which are only 1-qubit gates, and the first one is Hadamarding the first qubit, and the second one is Hadamarding the second qubit. and I'm getting a failure where basically when I try to run the circuit, it's saying internally my matrices aren't the right size to operate correctly on the qubits. So almost certainly the problem is something going on here, and so I'm going to write another test to handle that case. Sounds interesting. I know absolutely nothing about quantum computers. Yeah, neither did I really before I started this project. I'd studied quantum mechanics to some extent, and a big part of the motivation here is just to like wrangle with quantum computing as a way to understand both quantum computing better and quantum mechanics better. The brief summary, the thing that's different about a quantum computer and a regular computer. So if you think about a regular computer, it operates on zeros and ones, and so you can have a really simple model of what a regular computer does is you have some zeros and some ones that correspond to some input. Say it's the binary for the number 7, and then you want to add 1 to 7, say. You write a series of gates that operate on those ones and zeros, and they can result in the output of the binary for 8, 1, 0, 0. In a quantum computer, you do the same thing, but the qubits, they're not bits, they're qubits. They can live not only as a 0 or a 1, but they can also live as a superposition between the two, which is kind of like a blend between the two, except that it's a blend between the two that when you measure the value of the qubit, it's going to act like a weighted coin. So if it's a, like for instance, we have, we can create a qubit that's a mix with a left-hand weight and a right-hand weight, for instance. And if I just look at the test for this, so like this is a 1 to 3 weighting between a pure 0 qubit and a pure 1 qubit. And if you measured this qubit, you would now 1/4 of the time, so 1 out of 1 plus 3 of the time, you would get 0, and 1/3 and 3/4 of the time, 3 out of 1 plus 3, you would get a 1. And so you get this kind of probabilistic thing going on, but it goes one more layer than that because qubits can be entangled with one another. And so the qubits themselves can actually interfere with one another in a complex way that leads to the ability to, that's the really powerful thing that leads to the ability to run algorithms that regular computers can't. And in particular, the thing I'm working up to in this series is called Shor's algorithm, SHOR, and it's an algorithm for factoring large numbers efficiently. So obviously I'm implementing it on a classical computer, not a quantum computer. It will not run quickly on my computer, but if we could implement the same algorithm, and people have done it in like labs and things, and I suspect like IBM and Google and the tech companies that now have quantum computers, I suspect that they've implemented Shor's algorithm for like a small number of bits. So I remember seeing somewhere that somebody had done it. They had factored the number 15 into its factors on a quantum computer into 3 and 5, which is like, oh, I could have done that, in my head. But of course, they're demonstrating that it's possible to do with a quantum computer. And my understanding is that quantum computers are becoming a lot more realistic, and they're starting to get to operate on larger and larger data sets. So hopefully that's a useful summary. And let's see if we can solve this bug, huh? So I want to take this test. So just as a matter of sort of coding best practices, this test is doing a lot of things, and that's fine. I don't adhere to like really strict TDD or anything. But now that I'm trying to debug a specific issue, and I think I've got it localized to this call, I just want to set up the simplest possible test that tests that case. And so I'm going to test, let's see here, test adding, let's say, quantum circuit adds gates in the middle. And by the way, what branch am I on? Fourier transform. Okay, that's fine. Okay, so we'll create a circuit with that takes 2 qubits as an input. I'm actually going to make it 3 qubits just because I think it's a slightly more general case. And I'm going to add a single gate in the middle to the first index, 0, 1, 2. And then I'm going to run it on 0. And so a Hadamard gate. Whoa, wait, what happened here? Okay, I'm going to add a single gate, Hadamard in the middle. A Hadamard gate is one of these gates that can't exist in a normal, in a classical computer, because what it does is it takes a pure state, like the state that will always be 0, and it turns it into the 50-50 mixed state of 0 and 1, not a classical gate. So in this case, I expect the pure 0 state, the 0 basis state, to, when I run the circuit on it, I expect it to come back as, let's just say, expected is a mix of qubit 0, qubit 1 at a equal weighting. And then we'll just say expected here. And everything looks happy. Okay, so we expect this test to fail. Cargo test quantum circuit adds gates. Should be sufficient. Oh, it passes. Really? That is not what I expected. Very interesting. Okay. What if we add like a CNOT gate in the middle? Adds 2 qubit gates in the middle. So what if I do a CNOT gate, which is a 2 qubit gate, and then we'll start this off being a 4. Oh, also, wait a second. How did I even run? Hang on. I actually would have expected this to fail entirely. So, because I can't be running a circuit on a register that only has 1 qubit in it. That is a 3 qubit circuit. That should just fail. I'm very surprised that that didn't fail. I'm very surprised that that didn't fail. Takes 3 qubits. I added a gate to it. Like, this should end up constructing a 2x2 matrix. A 2x2 complex matrix, which gets applied then to a... No, sorry, it should end up constructing a 3x3 complex matrix that gets applied to a single qubit. No, it should end up constructing... Okay, so the number of qubits is 3. That means that the basis, which is the binary for any 3 bits, is going to be 2 to the 3, which is 8. So this should be an 8x8 matrix when it gets added, and then I'm applying an 8x8 matrix to a 2 vector, which should fail. I'm very surprised. I mean, we can make it fail faster, but like, we really should have this panic if the qubit isn't the right size. Let's get the inner register. And this becomes inner register, and we probably have to clone it. Don't need the N2 anymore, but we do need to clone it. Oh no, we don't. That takes it by reference. Okay. So that at least should cause the test to fail. It doesn't. Oh, that was the wrong test. Let's run the correct test. Not that one. This one here. Okay, good. That fails. And it fails for the right reason. Okay. I feel like I must not know something about how matrix multiplication works on the N-algebra matrices. Okay, so what we actually wanted here was the 3 qubit. So we wanted quantum gate, quantum register, not single, but basis, or from int, 3,0, the 3 qubit quantum register with all zeros. And then I guess I can do this slightly better and say all zeros, 3, a little bit nicer. And now I expect this to run. Do I? I expect it to fail because my expected qubit is of the wrong size, which it does fail, and it fails because of dimension mismatch. Let's jump into almost equals and have this fail for a better reason, namely, let's see here, assert equals that the qubits is the right number of qubits. This clone. I guess we can't clone there. Here we can clone. We have the same problem as last time though. Whoops. So let's do inner RHS and let inner RHS be RHS.inner. And then this gets cloned. Sorry, this should be into. And this becomes inner RHS. Okay. That will at least yell at us sooner, which will make it easier to test things. Cool, so this is still failing. It should fail with the new error message though. Or not with a new error message, but with a new specific. These things don't match. No, it doesn't. Okay, so now it's failing for the reason I thought it would fail in the first place. So my guess is that the reason that it wasn't failing was I basically had 2 bugs that were canceling each other out. So this is progress. Let me just finish implementing this guy. So we need this to be a quantum register so we need to just mix. We need this to be a quantum register that's a mixture of So the Hadamard gate is going to, applied to the middle qubit, should return a mixture, should return 1 over root 2 times 0, 0, 0 plus 0, 1, 0. Right, because it's going to mix the state that is 0 with the state that is, I guess that's 2. Yes. And so I should be able to do the same thing with a mixture of let expected be qubit register or quantum register mixture of quantum register from int 0 and quantum register from int 2. I know how binary works. Quantum register mixture takes 1 argument. Oh, these need to be in a vac. Okay, and then from int, I need to tell it how big the quantum register is. Okay. Cool, and now we get expected. Let's not stomp on expected. And now we expect that this will fail for the original reason that we cared about, which it does, because dimensions are mismatching, and we can use that to debug. Cool, and then let's just write this test also. So we expect if we pass in 0, 0, 0, 0, let's not do 0, 0, 0, 0, let's do 0, 1, 0, 0, and we expect that to go to 0, 1, 1, 0 because we've got a controlled NOT gate on these 2 bits. And so that's going to be let expected quantum register mixture, and we're going to mix 4 with a 6. That's correct. Okay. And then we're not going to run it on a singleton. We're going to run it on all zeros. No, we're going to run it on from int 4, 4. Oh, it's not going to be a mixture either. It's just going to be this. Okay. So we run it on 4, we get back a 6. Okay. And we expect this to fail for the same reason. Sweet. And the reason I'm constantly saying what I expect things to do is so that when they don't do what I say that they will, I stop and solve it. One of the places that bugs come from is when you just go, oh, the computer did a thing. That was probably what I wanted it to do, and you don't notice that there are problems. And wait, did I just do that? No, this did fail, right? Yeah, okay, cool. Sick. Okay. So let's figure out what is going on, and we're just going to use the debugger at this point, I think. So we think the problem is in, let's see here. Let's first take a look at what circuit looks like. So we expect circuit to contain 1 gate. We expect that gate to be an 8x8. What do we expect it to be? We expect to have 8 complex numbers in our register, so it's got to be an 8x8 matrix. which will have 64 entries. I'm going to get rid of the other breakpoint for the moment. And we look at circuits, we look at the gate, we look at the size of the gates, and it has only 4 entries. Okay, and this is why our test passed before, even though we were supplying the wrong number of qubits. So indeed, our 2 bugs were canceling each other out, the bug in the test and the bug in reality. Not the bug in the reality, the bug in the actual implementation. So the question is, why are we getting a 2x2 matrix instead of an 8x8 matrix? Let's take a look at what happens in add gate. I don't care about what happens in Hadamard. We know that's working. Couldn't open the binary. I find VS Code's debugger for Rust to be a little bit iffy, but that's okay. Let's just jump to here, which I think is where all of the action happens. Stop. Debug there. And then okay, so the point of the add gate function is we handled a case where it's just complete. It's a gate that completely spans everything. So like we have a 2-qubit input and it's a 2-qubit gate. That's fine. That case is really easy. But otherwise, we're going to have to tensor product in the identity. So basically, we have to take the core gate, and we need to, that might apply to 2-qubit input qubits, and we need to tensor producting in the identity gate is just going to expand it to be the right size. And so I kind of strongly think that somehow that's going wrong. So if we look at the identity gate that we construct has a length of 16, which means it's a 4x4 vector, which is what I would expect, because I would expect we're trying to turn a 2x2 into a 8x8, and so we need a 4x4 to do that. And then if I look at gate to add, it's been optimized away, which is annoying. There we go. Gate to add has length 64, so that's the correct number. Okay. So then we swap the bases. So we swap columns to put it in the right place, to put the elements of the matrix that actually affect anything in the right place. And so now we would still expect gates to add to have a length of 64, which it does. Oh, this is a dumb bug. Then we push the gate. We need to push gate to add. Okay, that would certainly cause the effect that we saw. So let's go run our test. Run test. Fails. Does it fail for a good reason? It fails because it doesn't agree with my output. Okay, so we solved that bug. There is a new bug, presumably, possibly just with my test. So let's go ahead and say actual clone here, and we will let actual be this, and then we'll output actual so that we can inspect it. And it fails because it says it says that the output is 1 over root 2, 0, 0, 0, 1 over root 2, 0, 0, 0. That's an 8-dimensional thing. So this is a mixture. It's saying that the result is a mixture between 1, 0, 0, 0, 0, so whatever that is, 4, and it's the first. No, so it's saying it's a mixture between the first basis vector and the 1, 2, 3, 4, 5th basis vector. The first basis vector is this. The 5th basis vector is not that. Is it? 0, 0, 0, 0, 0, 1, 0, 1, 0. No, it should be the 3rd basis vector. Interesting. This is notably the 3rd to the last. No, it's not. Okay, so we've successfully mixed 2 inputs. Just not the ones we cared about. So the bit, yeah, it should be the bit corresponding to, it should be 0 and 2. So this is 0, 1, 2. This one should be getting flipped. Okay, so why is it not? Let's go back into our debugger. Okay, so the indexes that we put in, let's see here. We sorted the qubits, so the sorted qubits should be still just has 1 element in it, which is 1. And now we're swapping 0 and 1. I don't think that's right. So this gate, so we're saying the Hadamard gate takes 1 input. It operates on a 2x2. That's a 2x2 matrix. Okay, we're not taking into account that the number of basis vectors that a n qubit gate takes into account is 2 to the n. That's the problem that we're running into. So there's something in here that's like, let's kill the debugger. There's something in here that's like, let's see here. So for each of the qubits that we want to swap, we then need to swap all of the inputs that correspond. trying to think. I'm pretty sure the one qubit case and the 2 qubit case are not that hard, and then I'm trying to work out how it generalizes to the 3 qubit case. So suppose we had a 3 qubit gate. Suppose it was operating on the 1, 2, and 3 qubits. The 3 qubit gate would be a 8 by 8 matrix. We would construct, say, a 16 by 16 matrix first, and then for all of the 2 to the n, so all of the 8 basis vectors, we would need to do some swapping. And the swapping we would do is just to swap okay. So we need to know the number of qubits. Do we already have that pulled out? Sorted qubits. No, but we can pull it out ourselves. But wait, what about in the bad case where we have, suppose we have like a 5 qubit circuit with 3 qubits, 3 qubit gate, and it's at 0, 2, and 4. It's a really nasty case. I don't know why I would ever do that to myself, but this function should be able to handle that. Then I have a 32 by 32 matrix. I know how to construct that matrix, but with the wrong bases. But the 16 by 16, or sorry, the 8 by 8, no, the 16 by 16. Oh, man. Let's see here. Nasty case. Circuit has 5 qubits. Gate has 2 qubits, and qubits are 0, 1, or 0, 2, and 4. Then matrix is, so circuit matrix is 32 by 32 times 2. It's 64 by 64. And the gate matrix is 16 by 16. Wait, gate has 3 qubits. 16 by 16. Need, what do we need? So we're gonna so the gate to add is identity for the first 4 by 4, then gate, then identity. Nope, not even. I wish GitHub would shut up, it's distracting me. The point is that the way that this function works is that it first assumes that that the gate applies to the first 3, or to the first n qubits, and it constructs the relevant matrix, and then we just swap a bunch of bases, the bases around until we get the right resulting matrix, and there must exist some swap that works. but it hurts my brain to work out which set of swaps that would be. I can do it in the simple cases. And part of what's awkward. Okay, we can simplify this, and it still, I think, is gross if it's like this. So now the circuit matrix is 16 by 16. If it has 2 qubits, no, it's 8 by 8. 8 by 8, and the gate matrix is 4 by 4. The point, though, is that the 4 by 4 that it should be operating on are the 4 that correspond to 101, or sorry, 000, 001, 100, and 101. Point is that the bases that the gate should operate on are 000, 001, not this one, and not these. Whoa, I still got one too. Not this one. So that to me means that I want to swap the identity matrix with the bases for, therefore swap the identity gate, the identity bases with 0, 1, 0, 1, 0, and 1, 1, 1. It's really 0. It's not really right, though. Let's write out what the circuit is affecting. It's a funny problem. Wait, I'm still missing bases in here though. Zero, 1. How about this? The point is that with respect is that the matrix, the gate doesn't see differences between, e.g., 0, 0, 0 and 0, 1, 0, or 1, 1, 0, 1, 0, 0, and 1, 1, 0. Okay, that seems relevant. So what does that mean? If it doesn't see differences between those, then we know that it acts on those the same way. So this is the 0th position. This is the 2 position. And it acts on those identically. And this is the 4 position, and this is the 6 position, and it acts on those identically. And so the thing that acts on this basis vector is the 0th column of the matrix. The thing that acts on this one is the 2nd column of the matrix, the 4th, the 6th. And when I Kronecker product or tensor product gate with the identity, it's going to look like I think it looks like an identity matrix with the gate put in each of the coordinates. Is that right? Let's take a look. Let's take a look at what Wikipedia thinks about Kronecker products. No, it's going to look like it's going to look like a matrix of identities times each of the coefficients in A, which means that the symmetries are what? Which means that if B is the identity matrix and it's a 4x4 matrix, then every 4 columns is identical? No. It means that the first 4 columns are identical. Nope, that's also not true. It means that let's see here, this column hits the first basis vector. This column, next column hits the second one, and so this column hits the first basis, this hits the second, and so on. And so if we know that we want certain basis vectors to be treated the same way, we have to know more than just the shape of the Kronecker product, because in principle none of these columns need to need to be the same, right? In the most general case, so this column operates on the zero basis vector, the first basis vector, and so on. But in principle, depending on what A and B are, there don't need to be two columns that are the same. And even if B is the identity matrix, they still don't need to be the same. Because if B is the identity matrix, then nothing within B is the same. Every column is different, and then the coefficients being applied are different. So do I know something about my A matrix that will make everything symmetric again? My A matrix corresponds to the gate, and the gate is unitary. Unitary matrices are equal to their own transpose. They're equal to their conjugate transpose. They're equal to their conjugate transpose, but that still doesn't make it seem to me like there's an obvious symmetry. Okay, so let's look at our search. So let's just put in something that has the right number of swaps, and then let's look at the circuit and see if we can tell from a particular circuit what the pattern is, because I'm struggling to do this from first principles, and I'm sure it's just that I'm not quite thinking about the linear algebra right. Okay, so let's see here. So the thing we know, though, is that we're going to need to do we need to do swaps for each of the identity matrix lengths. Yeah. We need to do one swap for each 2 to the n. Okay, so let n swaps be identity gate dot n qubits. Can I just do size here or something? Is size a thing? No. Length? No. I thought I had something there. We'll say 2 dot power to the n qubits. And then whatever, this should be a U size. And expected U32. Oh, that doesn't work, does it? Needs to be cloned here. And then we're going to go from 0 to n swaps. And I mean, there really should only be like one natural choice for this. So we're going to swap the ith index with it can't be the sorted qubits. It has to be the leftover ones. I don't know, let's just put IDX in here for the moment. And then let's take a look at what happens to our tests. Okay. So we expect this case to fail because the swap happened with the wrong one. So in this case, where did we want the swap to go? We wanted it to go against the third basis vector, or the index 2, right? Index 0 and index 2. And why is that what we want? It's because those are the two. It's because that's the difference between the first input qubit being flipped and not. That's why. So the two that get flipped are should be so we know we're swapping two bits, but one of them should be the trivial flip of 0 and 0, and the other one should be the flip of 1 to 2, because 2 to the 1 is 2 for binary. So we want to raise the we want it to be for all values of this. That's what it is. That's what it's going to be. Okay, so we want to swap all values of these qubits with the first n qubits. That's what it is. And then for this one, we're going to swap 0 with the 0, 1 with 2 to the with the second qubit flipped. Wait, would we flip this one or this one? We want 1 to correspond to this one, and then we want 2 to correspond to this one. Yeah, that's what it's going to be. That's what it's going to be. Okay. Getting there. All right, I don't need my nasty case anymore. This is how many swaps we're going to have. And then we're going to... I don't even think I need this anymore. I think what I need is for IDX in 0 to sorted qubits dot length for J in 0 2 let me index IDX to swap is 0, IDX to swap plus equals 1, needs to be on the innermost loop. And then this isn't going to be an index. This is going to be, we can call this the qubit index. And then this will be the see here, for each qubit index, we want to do something with both 2 to it and 0 to it. It still isn't quite right. I want to count in binary on only the qubits that are in my sorted qubits. So the index to swap is going to keep incrementing by 1. But then the destination index is going to be either the previous qubit with the qubit index incremented, or okay, here we go. Let me destination qubit indices be a vector. Qubit index we won't need to capture this yet. And then for each qubit index we go through, we need each of the previous ones, each of the previous destination qubits. And then we also need to add in all of those plus the new qubits. So let's let like new bit value be 2 u size power of the qubit index, and then destination qubit indices is going to be destination qubit indices plus the new bit value, but I also need it to be plus itself. Which I have a feeling for destination index in qubit indices I want to push destination index plus new bit value. And it hates this because oh, it doesn't hate this. I'm surprised it doesn't think I'm trying to move this twice. Oh, it's going to think that. Okay, and then for I in 0 through destination qubit indices dot length, we want to swap columns. Let's call this IDX, and we just say don't really need this, I don't really need this, and we will swap destination qubit with IDX. Okay, so certainly that, and this is swap bases, certainly that is the right number of, and this mutates in place. That's the right number of swaps. And I believe it's correct. But we'll find out. Okay, and one thing it doesn't like, yeah, is that I'm moving this value. Can I not move this value? It is also borrowed as immutable. That is fair. Let's just clone it. Let mute. Actually, mute. Can I do this? U size can't be added to a mute U size. Yeah, that's not the problem though. The problem is that doesn't make my vector immutable. Oh, how about 0 dot dot length, and then destination qubit indices dot IDX. There we go. Okay. Let's see if that does it. It does not. So we get, wait, let's do the simpler test first. Okay, so we get the Hadamard applied to 0, and again it's being applied to 5. Whereas we think it should be applied to 3. Add gate. So okay, let's do the test and just walk through the logic again. Whoops. It's not letting me trash these. Okay. So we are saying the new bit value So if it's empty, though, this doesn't quite work. We need to instantiate the initial vector with just 0. But then we're still going to have one swap. But now if the index is 0, we will get 0 swapped with 1. That's not right. Let's see here. In the simplest case, we just want to do 0 and 1. Maybe this is right. So if you put in, if the only index is 0, then 0 and 1 are going to get swapped, which is fine. No, it's not fine. 0, it should be 0 and 0 get swapped, and 1 get swapped. Is that what's going to happen? Maybe that's what's going to happen. Yeah, I think that's what's going to happen. Okay. Let's find out. Okay, fails. 0, 1, 2, 3, 4. Okay, still failing for the same, on the same thing. Okay, so now destination qubit indices has 0, 1 in it. Which is not right. We want it to have 0, 2 in it because we want it to take 0, 1. We want it to take 0, 1 and new bit value. So this is essentially, this is going to be 2. And then we already want one to be in there. We already want 0 to be in there. So 0 is already in there. This should evaluate to 2. It does not seem like it evaluated to 2. Why not? Let new bit value. Oh, this should just be sorted qubits. Still same issue. New bit value should be 2. It is. So now destination qubit indices should be 0 and 2, which they are. Destination qubit we're doing the swapping with what we expect. But now let's look at what gate to add looks like. It is complicated. Okay, this seems really difficult to tell what it says, but here we can look at what actual is. Well, we know what actual winds up being because it's what shows up in the final test, and it's wrong. Why is it affecting the 5th bit? Like, at all? So the 16 by 16 matrix is 16 columns that work on each of the basis vectors. The basis vectors we want to affect are the 0 and the second basis vectors. We are swapping the 0th basis vector with the 0th basis vector and the first basis vector with the second basis vector. In the matrix, which really you would think would affect 0 and 5. Okay. Okay, so 5, interestingly, is so like if you take our 8, if you think about our 8 basis vectors, so if you read the binary backwards, then this makes sense, I think. Because now, if you count 0000, 0001, 010, 011, 100, that's the 5th element here. And 100, 100 is 001 backwards. So we're just, our bits are backwards someplace. Okay, so where are our bits backwards? So when we swap bases, let's see here. So in my quantum registers, if I do a basis vector, Where are my quantum register tests? Test quantum register instantiates bases. So if I want to assert that quantum register basis 5.2 almost equals quantum register new or from back not this. I want that to be this also isn't basis, it's from int. I want that to be complex 0, complex 1, and then a bunch of complex zeros. Because this is for sure the convention that I want to read stuff off as, where all I have to do is look at whether there's a 1 in the ith location. Perfect normalize. And what's wrong with my parentheses? Okay, making progress. Wait, what? Back normalize. Wait. This is a vector with 8 elements. From int. 3 is what I want. Failed. And let's find out why it failed. Hang on. 0, 0, 1, 0, 0, 0, 0, 0. Well, that's clearly not what we want. Oh no, it is. It should be 0 indexed. Okay, so this is working right. Okay. So that's not the problem. So is it swapping bases? So when I swap bases, test, quantum gate swaps bases. And what should that mean? Let mute gate equal quantum gate C naught gate dot swap bases 0 0 assert gate almost equals quantum gate C naught gate swap bases 0 1, and now we don't want to almost equal the C naught gate. We want let's see here, let 0 0 be quantum register. We want these things, and then we want to assert applying to 0 0 should no longer give back 0 0. It should give back 0. Oh no, it should. Zero 1 should give back 1 1. 1 0 should give back 1 0. And 1 1 should give back 0 1. Because it's a controlled NOT gate, except it should be flipping the other one. If we run this, it fails. It fails on the second line, because somehow it has failed to swap bases effectively, I guess. Sure, because all it's done is poke at its coordinates, right? It's just swapped one column, but that's not what swap bases should do. Swap bases should do the thing that we just wrote up here, I think. Maybe. It can't just swap two columns. It has to swap all of the columns. Has to swap the columns that correspond to 0 and 1 in that basis. So it should be let I sub 0 is 2 U size power of, wait, I sub 0 is always 0. Let I sub 1 is always 2 U size power of I. J0 is 0, J1 is power. and then we say new matrix, self.matrix, clone dot swap I sub 1, J sub 1, and then self dot matrix is new matrix, and we can get rid of these lines. And this is swap columns. Hey WYLD, what I'll make in the end is a way to simulate quantum algorithms. So the thing I want to get to is Shor's algorithm, which is a quantum algorithm for factoring large numbers. So we'll get to being able to implement that, and then also being able to visualize what the quantum algorithm actually looks like, what it's doing. So there's some clever ways to visualize complex numbers. So I'd want to basically be able to have something that you can easily construct any quantum algorithm you want, and then visualize it so that you can see what it's doing. That's the idea there. Okay, doesn't need to be mutable. Okay, so now swapping a basis, you put in which qubit you want, which qubit indices you want to swap. And so let's make sure that we're actually doing that. Let's actually call this qubit I and qubit J. This whole thing where you have to keep track of whether you're talking about qubits or basis vectors is a little bit tricky. And I actually think I want to call this swap qubits. And then in quantum circuits, can we just does this work now? For qubit IDX in sorted qubits. Gate to add, swap columns. IDX, qubit IDX. Very suspicious of this. Hang on, before we try that, let's try our qubit swap test. It's not even succeeding. don't think this is how I want the API to be. Swap bases. And then this will be basis I and basis J. And then all it does is swap the columns. I and J, which swaps just how the ith and jth basis are being treated. And so then in here, and then, so if I swap how the I and jth basis are being treated, this test doesn't do a good job of testing that. Because that's not what this says. This says treat 0 as though it's 1 and vice versa. So 0, 0 maps to what 0, 1 would have mapped to before, which is just 0, 1. 0, 1 maps to what 0, 0 used to map to before, which is 0, 0. And then these should be 1, 1 and 1, 0. Okay, and that works. So, back to the main test here. In our test, we want to swap how how the basis vectors, how the first n basis vectors are being applied to the first n basis vectors, where you skip over the bits that you need to skip over, like that are the identity, that aren't inputs to your gate, which are 0 and 2 in my test. And so isn't that what I'm doing? Swapping how the 0th basis is treated with the 0th basis, and the first basis with the second basis. But then when I apply that in the test, to the 0 state. So this should map 0, 0, 0 to 1 root 2 to the mixture of 0 and 1. Or 0 and 2, rather. That's not what happens. Even though, do we know that this works for the trivial case? Maybe we don't. Where's this going wrong? My serial quantum circuit. Okay, so my serial quantum circuit is working. My 2-gate quantum circuit is what's not working, but we don't actually know if the adds gates to the top, new qubits 3, 0, and then if I map 0, 0, 0 in there, I expect to get 0, 0, 1 mixed in. So 0, 0, 0, 0, 0, 1. Even this is failing. Fascinating. It's failing and it's hitting the same issue. So new bit value should be 0. New bit value is 0. And so the destination qubit indices are 0 and 1. So the issue isn't the swapping logic at all. Now. The issue is that this gate somehow doesn't do what I think it should do. But that seems crazy. Because we had working tests before that said that this gate did do what I expected to do. Do I have my identity backwards from my gates? To find a better way to keep my test things clean. So this still works with a serial quantum circuit. Does not. The linker failed. That doesn't seem good. Oh, it's because I'm in a test. That passed. That failed. Okay, so adding to the top now passes. Okay, so now we're getting somewhere. This failure is basically our swap didn't do anything. Why did our swap not do anything? So destination qubit bases. 0 and 2. Seems like the right numbers. So I would like to swap index 0 with index 0. index 2 with index 2. Or index 1 with index 2. And now push the result on. Like, very skeptical of this, though. I don't really believe that this is the right way to look at this. Wow, I'm running out of time too. And I've spent this entire session on this issue. That's disappointing. Okay, but this... Did this actually solve something? Is there a test that's passing now that wasn't passing before that yeah, this one. This one is passing now. And in this one we do no swapping. So the swapping logic is failing, but the gate logic is passing. Is it the inverse here? I'm gonna guess at a couple of things. Register size, 2e size power n qubits. Register size minus this and IDX, and register size minus IDX. So this still passes. Nope, fails. How can that fail? I didn't. Oh, the code does run on that. Do I have to do -1 there? Yeah, I have to do a -1 there. -1. -1. Then this guy still fails. It had no impact. Kind of feel like I need to switch the 5th, given what I've seen. Instead of switching 0 and 2, I feel like I need to, or 1 and 2, I need to switch 1 and 5. Because the The point is that if I take my basis vectors, it's not that 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 need to get mapped. It's that 0 should stay the same, 1 should stay the same, 2 should become these still aren't the right basis vectors to be swapped around. It's that 0, 0, 0 should go to 0, 0, 0. 0, 0, 1 should go to 0, 0, 1. 0, 1, 0 should go to 1, 0, 0. 0, 1, 1 should go to 1, 1, 0, 1. 1, 0, 0 should go to... yeah. That's what we want in this case. And that takes 4 non-trivial transformations. It takes 8 transformations total. So for each of the gates qubits, I should want to swap them somewhere. But some of those swaps might be trivial. This is each of the gates qubits. For each of the sorted qubits. Hey Draco, thanks for following. I'm fighting through an issue that is making my brain hurt, which is working out for a quantum gate that is some size, adding it to a quantum circuit that is potentially bigger. And that involves some linear algebra. And every time I have it, I think I don't quite have it. And I need to end in the next 15 or 20 minutes, and I'm very close. Very close. So, I hope things are good with you, though. So, the point is that for each of my qubit indices, I want to transform so my qubit indices are 0 and 3. This is the 0. This is the 0 qubit. This is 0, 0. This is 0, 1. This is 1, 0. This is 1, 1. Which is to say, these. And if I just swapped those 4, I would have swapped everything. Yeah, because these would stay the same. These would get swapped. Okay. So I only need to make 4 swaps here for this particular case. So for each qubit IDX, I want to take 0 and 1 and apply those to every previous qubit. And so that's going to mean that I can reconstruct a new version of the vector that has zero and 1, has the old vector and then the 0 version of it and the 1 version with the new leading 1. Which I sort of feel like is what I'm doing here. If destination qubit indices dot length is 1, then destination qubit indices dot push 0 and destination qubit indices dot push new bit value. Otherwise, take whatever we previously had and push some new versions of that on there, which I think is going to be equivalent in my case, though. So that should make these 4 swaps. And these 4 swaps should make whatever you used to be doing hang on, this is the qubit for 2. The qubit for 2 doesn't change. This is the qubit for 1. Never mind. Okay, the qubit for 1 does change. Should still pass. And then this one should still fail because I don't think I did anything. Still failing for the same reason. It's a mixture between 0 and 1. This is a mixture between 0 and 1. But wait a second. But I'm saying in my example that 1 gets mapped to 1. It doesn't get changed. So why do I think it should? A Hadamard gate applied to the only the second qubit means that it mixes applied to 0 should mix 0, 0, 0 and 0, 1, 0. Which is a mix of 0 and 2. I believe that. I do. I believe that that's true. And my test tests a mixture of 0 and 2. Okay, but then I'm also saying that this should be the basis shift. But that seems obviously wrong. A Hadamard gate, the default is for 0, 0, 0 and 1, 1, 1 to get mixed, or in 0, 0, 1 to get mixed. I'm so close to cracking this thing. I can feel it. The default is for 0, 0, 0 and 0, 0, 1 to get mixed. So we need 0, 0, 1 to get mapped to 0, 1, 0. Zero, 1, 0 should still be mapped to 0, 1, 0. 0, 1, 1 should get mapped to 0, 1, 1. 1, 0, 0 should get mapped to 1, 0, 0. 1, 0, 1 should get mapped to 1, 1, 0. 1, 1, 0 is fine, and then 1, 1, 1 is fine. So the point of this is that the 0, 0, 1 state needs to get mapped to the qubit index turning into 1. So anytime that you have a 1 in a gate, anytime that you have a 1 like the gates are getting left, right, read right to left, basically. And I think that's what we're missing. Wait, this doesn't make sense though. 0, 1, 0 has to go to 0, 0, 1. 1, 1 is fine, 0 is fine, that's fine, and this needs to go to 1, 0, 1. So in this case, we need to swap 1 for 2 and 5 for 6. Which is something like 4 gate index in 0 through self dot through sorted qubits dot length. Let gate 0 equal 0. Let gate 1 equal 1 to the gate index, sure. Let qubit 0 be sorted qubits. No, just be 0. Let qubit 1 be 1 to the sorted qubit gate IDX. And then gate to add dot swap gate 1 qubit 1. Can't be this simple, can it? Oops. Swap bases. Still fails because gate 1 is zero. We want this to be 2 to the power of gate IDX. Which is going to be 1 here. This is -1 plus 1. Sort of qubits gate IDX. So now this is going to be 1. This is going to find me the starting. This is going to find me the index, essentially. And then this is going to make it equal to 1. The qubit 0, I think qubit 0 is important though also. It's going to be this. And so I think, is it this? So then gate 0 and qubit 0. And we do gate 2. Add swap bases gate 0 qubit 0 gate 0 qubit 0, yeah. Tempted to subtract with overflow. This should be 2 to the power of 0 minus 1. Well, something happened, but it's not right. This still runs okay. Okay. So we find that the gate index is 2 to the 0, which is 1 minus 1 is 0. So we're talking about the 0th basis state and the first basis state, which seems right. And then we're swapping that with the first basis state. So 0 is getting swapped with 1, which is not right. 0 should get swapped with 0. Are these just always 0? Gates. The gate's 0. The gates 0 and the qubit 0 are always going to be the same. The gates 1 and the qubit gates 1 might be different. And then we have to keep going. These are always going to be 0. Then this is still failing because we're swapping we need to swap 1 with 2. Is this 1 and 2 yet? Two to the power of 1. So this is 2. It should be getting swapped with 1. So this should pass specifically this test, which it does not. Because even though this is in the 1 position, it's not getting swapped. Gate 0 is 0, gate 1 is 1, and qubit 0 is 0, and qubit 1 is 2, which is exactly what we would expect. So swapping basis on this just isn't doing what I think it should do. Okay, well, I'm gonna look at this off stream some because I've spent a long time on it already, and I don't think it's that fascinating to watch me wrangle with the linear algebra here. I don't know if there's, I feel like there's a takeaway here in terms of like how I'm approaching debugging this. I feel like I've been stabbing a little bit. But sometimes there are these problems that have this flavor of like, you just feel like you're really close, like off by 1 errors often have this flavor, right? You're just like really close, and all you want to do is just like add +1, -1 everywhere until all your tests pass. And like honestly, that sometimes is the fastest way to solve it. You probably learn less, but you solve it that way. And this has that flavor where it's like all I need to do is make this happen. It seems like, but I've been really struggling to do that. So anyhow. We're gonna call it there. Let's see if anybody's online to raid. Nobody super relevant here. So we'll just end it here. I hope everybody had a great weekend, or is going to have a great weekend, and I will probably solve this off stream and then let you know what the solution was and how I would have approached it better at the beginning of next time. So, all right, catch you later.